This week we cover electrophilic aromatic substitution, or EAS reactions. We have discussed why aromatic rings are stable. We've seen that they do not behave like normal alkenes. And so we're going to take a look at the reactions that they will perform. You will notice that these, again, do not act like alkenes. We are not doing addition reactions. We are doing substitution reactions. So these are going to look a little differently. In this first reaction we're going to do a bromination, and the Br is going to substitute onto the ring. We're using benzene, very simple aromatic ring. And first I'm going to show you how the Br2 and the FeBr3 react and form the complex that will react with the benzene ring. So to start, the bromine will attack the iron complex, and it will attach there. So we now have our new iron complex. There's a positive charge on this bromine, and there is a negative charge on this iron. We all know that bromine does not want positive charges on it, and so we're going to see something interesting occur. What will actually happen is this bromine in the center here is going to want to pull electron density away from the end bromine. And so what we're going to see here is these electrons will want to jump away and pull away, and it'll leave this bromine with only 6 valence electrons. Again, that is a positive bromine, and then you're going to end up with FeBr4. Okay, so FeBr4 is made. Negative charge on the iron. So this is electrophilic. And it's going to want to find a nucleophile to attack it. On the next page, we're going to see this actually occurring. The bromine, one of its pi electron sets, is going to go out and attack this electrophilic Br position, and we are going to see those electrons pull away and fix that positive charge on that center bromine. When that happens, we haven't fully completed our substitution reaction. We form what we call a sigma complex. The sigma complex is a structure that has lost its aromaticity. It is no longer stabilized through that aromaticity, and it is only able to do resonance through part of the ring, because now this carbon here has switched from sp2 to sp3. And so we're going to have to draw resonance. This is a big chapter in regards to resonance, and so anytime you see a chance to draw resonance, it's good to practice. So I'll show resonance being drawn here. And so we get 3 possible resonance structures for the sigma complex. Okay, now that resonance does stabilize the sigma complex, or help stabilize it, and allows it to form, but you still have to remember this jumps really high in energy. So the activation energy for these are, you need quite a bit of energy for these to occur. Reason being, again, is because your aromatic ring is stable, and the reason that these reactions will occur is because we are going to reform that stability in the aromatic ring. All right, so I'm going to pull out the sigma complex again and finish off this reaction. So we have one of the resonance structures, and what's going to happen is that bromine is going to end up coming off the FeBr4 and remake FeBr3. So we have this bromine ion floating around, and it's going to deprotonate this hydrogen here where that carbon switched to sp3, and we are going to reform the aromaticity in the ring. So we'll get HBr formed, and the aromatic ring returns. But this time, instead of it being bromine, it's now bromobenzene. Okay, and again, the carbon right there switched back to sp2, so it's all back to normal, and it can do resonance.